In this video, we start to look at the fundamental theorem of calculus. Hopefully you've taken some time and looked at this in the notes. As we go through the steps for the proof of this, we're now going to use the result known as the fundamental theorem of calculus. First, let's state what it is, what it says. We say let capital F be an antiderivative of little f of x. Then it turns out the definite integral, the integral from a to b of f of x dx, is actually just capital F of b minus capital F of a. In other words, we take the antiderivative and we evaluate it at two endpoints and subtract them, and that will actually give us our definite integral, whether that would be area beneath the curve, or if it's a function that's both positive and negative, then it would be the difference between those two areas. This will actually work it out and evaluate it for us just by looking at the antiderivative, and that is a really big important thing that allows integral calculus to kind of go forwards. Otherwise, we're stuck with those little sums. And we really only looked at a limited class of functions. First, second, third power polynomials. And that was it. We were able to kind of sneak in the square root of x. But otherwise, we were kind of very limited. And so the fundamental theorem of calculus, this connection between an integral and the antiderivatives, is a really big accomplishment and a really big fact that now makes doing a lot of these problems, which would have been very hard before, a lot easier. Let's consider one example first, which is one we've worked out a couple times using sums. Integral from 0 to 4 of x squared dx. So we find an antiderivative. Turns out any antiderivative can work. And since we're going to be subtracting them, we choose the one that doesn't have a constant with it. Because when you subtract them, the constants would have ended up subtracting out anyway. So if this was 1/3 x cubed plus 4, then when you subtract them, the plus 4s would subtract out anyway. And then the notation we use is bracket, 0 at the bottom, 4 at the top. That means plug the 4 in, get an answer, plug the 0 in, get an answer, and then subtract them. So we do that. 1/3, 4 cubed, minus 1/3, 0 cubed. Well, 0 times anything is 0. So we just get 4 cubed, which is 64 over 3. And so our answer is 64 thirds. The same answer we got when we worked this problem out using sums. Let's consider a second example. Integral from 4 to 9 of square root of x dx. Now we did the integral from 0 to 1 of square root, and we were able to leverage 0 as one of our points to kind of make that problem work. For 4 to 9 would take a lot more adjustments and it would be more complicated. But now, using antiderivatives, we can do this very easily. First off, rewrite it as x to the 1/2 so that we can use our power rule. We add 1 to that 1/2, which would make it 3/2, and then divide by 3/2, which would be the same as multiplying by 2/3. So we'd get 2/3 x to the 3/2, evaluated at 4 and 9. And then we go ahead and plug both 4 and 9 in. Get 2/3 times the square root of 9 cubed minus 2/3 times the square root of 4 cubed. Quick little moment here on this square root. 9 to the 3/2 you can think of as square root of 9 cubed like I've done, or we could raise 9 to the 3rd power first, then do the square root of it. It turns out you can do it either way. I think it's a lot easier to do the square root than cube the answer, and that's what I've done here. So square root of 9 is 3. 3 cubed is 27. 27 times 2 would make that 54 thirds. And then square root of 4 is 2. 2 to the 3rd power is 8 times 2 would be 16 thirds. 54 minus 16 thirds would be 38 thirds. So it turns out the definite integral here, and because square root is always above the x-axis from 4 to 9, that actually is the area beneath that curve, is 38 thirds.